Again, using that script up above, using the context. Again, I'm trying to keep it in a nice, same context that the homework is going to ask you to interpret the confidence level using all of the verbiage from the problem at hand. There's always shorter ways to do it. You know, if many samples of red-eye piranha were collected and we constructed a 99% confidence interval using each sample, about 99% of these intervals would capture the true mean length of red-eye piranha in that river. So there's ways to shorten it down, but I wanted to make sure I try to keep as much context. That way when you're picking in your homework what matches, you know, I hope that helped out with Friday, keeping that script about interpreting the confidence interval as we did that. Let's do one more, let you get ahead of me. That way we can have one more on the video. The time for homework, again, I'll let you go work ahead. The principal of a large high school wanted to know how much time students spend during doing homework during a typical week. Based on a random sample of 100 students, a 90% confidence interval for the true mean amount of time doing homework for all students is 2.3 hours to 4.1 hours. Interpret the confidence level. Okay, so let me give you a moment to kind of work ahead using the script. Remember, you can scroll up and down. We're back to using means, so we're almost using the same terminology like we did on the last one. If the principal selects many random samples of students and constructs a 90% confidence interval, using each sample. About 90% of these intervals would capture the true mean amount of time doing homework per week for all students of the school. So he found 2.3 hours to 4.1 hours per week. 5-day week. 2.3 hours, that would be what? 120 minutes plus 0.3 would be 18, so that'd be 138 minutes a week at a minimum. So divide that by 5. Then you're saying on average 20-something minutes a day. About 28 minutes a day. Is that a lot of time? I don't think so. if I'm saying on average from 28 minutes a day to 4 hours would be 240 minutes. So you're looking at 50 minutes. So from 28 to 50 minutes a day, so no more than an hour is what they're spending on homework in a typical week per day. All right, so again, using the script up above, just to remind those on the video, we're just interpreting using this script and using the context of the problem. Again, a lot of different ways you can rewrite it. You can stick with the way that is written there and then just put your context at the end. It's whatever you want. They just decided to use, instead of we, they specified, what group. What was the name of the group specifically in each problem there? So, again, another one there if you want it. Going to get into what affects the margin of error. There's two things that affect the margin of error. How do we make the margin of error wider? How do we make it smaller? We learned about it in the video about certain types of confidence intervals have a really wide margin of error, and some have a lot smaller. And so one thing to make it, as we look at it, we prefer a small margin of error. So if you decrease the confidence level, so in that first part there, is they say that if we went from a C level of 95% to 85%, the confidence interval, or the margin of error, gets smaller, and therefore would make the confidence interval not as wide. So the CI not as wide. Okay. If I decrease, that's what the first one says. If I decrease the confidence level, then my margin of error gets smaller. My confidence interval is not as wide. So if I go from a 99 to a 90, if I go from a 99 to a 98, doesn't matter how much I drop. If I am decreasing the confidence level, then that means my margin of error gets smaller, and in turn makes my confidence interval not as wide. The other thing you can do to make your margin of error smaller, or make your confidence interval not as wide, is you could increase the sample size. So changing n equal to 5 to n is equal to 10, or n is equal to 50, makes confidence interval narrower, because margin of error decreases. Are you focused? Again, there's two ways to make your margin of error get smaller. Change the confidence level by making it smaller, or increase the sample size. We saw the effects of the sample size back in our previous chapter, going from n is equal to 2 to 10 to 20 to 30. We saw that it got not as wide of a normal distribution. It got narrower. Same thing applies with our confidence intervals. Now remember, the opposite could take place. If I increase the confidence level, I make the margin of error bigger. I make the confidence interval wider. If I decrease the sample size, I make it wider. I make the margin of error bigger. And you're going to have some questions like that. Okay, so you got to be able to go both ways. All right, so they asked us in these two examples, this example here with the fries, for us to explain what would happen to the width of the interval if the confidence level were increased to 99%. So let me get you to take a stab at it to see if you're okay with it. So in part A, what would happen to the width of the interval if the confidence level was increased to 99? So we went from 95% to 99%. So we know if we went down, it gets smaller. So since my confidence level increased, since sea level increased, the interval is wider because margin of error increased. Part B, explain what would happen if the width of the interval, if the sample size was increased. So n is equal to 3626 increased to 5,000. N increased, so it is narrower because margin of error decreased. Now, why does it in that case, why does it decrease? Well, it goes back to the formulas. When n is a bigger number, then that means I get a smaller decimal as an answer. Okay? So as I make n get bigger compared to what it started with, as n gets bigger, that means when I divide my fraction out, I get a smaller answer. All right? And then the reverse happens. As n gets smaller, then it becomes, as we approach, I wouldn't say we approach like an improper fraction, but basically I would have a bigger number on top than what was on the bottom, so it would be a bigger answer compared to when it was bigger. So that's kind of the little pieces behind it. We get to solve in the next couple lessons the aspect of solving for the minimum sample size to achieve a certain margin of error. That's what we get to do in the next couple lessons. So real quickly, answer that one about the Piranha, then we're going to move on to the next lesson. What would happen if the level was decreased, and then what would happen if you decrease the fish? All right, did you say something along this lines? If I drop in confidence level, I get a smaller width. The width would be more narrow. Sample size, if I decrease my sample size, it actually gets wider. Now, the one thing we got to remember before we switch over to the next lesson, the margin of error does not account for any source of bias. So that was that third bullet point when it talked about the non-response bias or there's different types of biases there. Margin of error does not account for any of that type of stuff. All right, next lesson. Oops, I want to add a page. There it is. All right, so in 8.3, we're estimating a proportion. As we go through and we learn how to calculate a confidence interval, we got some technical parts of a formula today. The second bullet point you have not seen yet. First thing we're going to do is check the random and large counts. We have done this before. If we meet the random condition and the large count condition, then I can perform a confidence interval. And so tomorrow we get to actually just do a 4-step process from the beginning to the end of finding a confidence interval. But before we can actually calculate it and interpret it, we got to see, do we meet these conditions? First, we're trying to see, do we meet the random condition? Was a random sample generated? Second condition, large counts. When we're dealing with proportions, that's the part where we're looking at n times p is greater than 10. Is n times 1 minus p, is it greater than or equal to 10? We're going to learn about critical values today, how to calculate them. I'll show you both with Table A and with technology. And then we're going to calculate a confidence interval by hand today, is what we're going to go through and do. Show you all the parts of it and how they come up with it. We'll learn a faster way tomorrow, so please bear with me. Don't experiment in the calculator trying to figure out what we're going to do tomorrow. Just need you to focus on what we're doing today. So, to construct a confidence interval for P, the population proportion, we're checking the following conditions. First, are you random? Did it come from a random set of data of the population of interest? And then second, is both n times p hat and n times 1 minus p hat, are they at least 10? Now, I need to explain something real quickly on this part, because when we did the previous chapter, we didn't use p hat when we multiplied it by n. We used what letter? Yeah, we just used p because we had the population proportion. A lot of times in what we're dealing with in this chapter and the next chapter, we may not have the population proportion. We may have the population mean. We may not have mean. So with that in mind, as I'm doing a study, and the reason I don't have it is maybe we're talking about all U.S. adults. Well, can I gather all the information from all the U.S. adults at one time in a feasible manner? No. So that's why we break it down to a sample, and from the sample, once I do stuff on it, then can I infer it to the whole all U.S. adults? Okay, so with that in mind, it's important that we get a random sample from whatever if we're going to infer it to a greater population. And so with that in mind, since I don't have the true population proportion, then I'm going to use a sample, is what I'm going to go through. I'm going to use the p-hat. Because as we looked at our interpretations on Friday, we said that, hey, we're blank % confident that the interval from this to this contains the true population proportion. Okay, so with that in mind, we're instead of when we go to test the large count condition, we're going to test the large count condition based on if they give me a sample percentage, saying, hey, from this sample, 85%, or maybe they give me a situation like 15 out of 30 people, okay? And so we use that for our p-hats as we check these things. So first couple examples, we're just checking the conditions. Do we meet it? So the Census School Survey selected 227 kids randomly. 84 reported they have allergies. We want to know, can we do a confidence interval? Well, do we meet the random clause? Do we meet the large count clause? So they tell us in the very beginning it's a random sample was selected. So they told us random sample selected. That's all I have to write. Hey, yep, we did it. And then the next part, they say, okay, large count. So is n times p hat greater than or equal to 10? And is n times 1 minus p hat greater than or equal to 10? All right, so with that in mind, we know that p hat is 84 out of 227. Don't divide it because it's a long decimal. And n would be 227. So we're going to say, all right, is 227 times 84 over 227, are you greater than or equal to 10? Well, the 227s cancel. Is 84 greater than or equal to 10? Yes. And then I'm going to do the other one. Is 227 times 143 over 227. How did I get to 143? Yeah, I just subtracted 84 from 227. That's how I got it. And then on this case, the 227s cancel, and I get 143 is greater than or equal to 10. Yep. So since both conditions pass, we can calculate a confidence interval. If you fail one of the conditions, then you can't do it. So if they don't tell us that it was a random sample, if they don't tell us that an SRS was compiled, then I failed the random clause. And therefore I should not do a confidence interval. Especially if I'm going to infer this to a bigger population and make some decisions based on it. If I don't meet the greater than 10 condition, then I don't do it if I fail it. Okay? We use these same conditions not only in this confidence interval chapter, but also in our hypothesis testing chapter, next chapter, and also in the chi-square stuff. So the next 3 chapters, this one and 2 others, all use these large count conditions. They all use these random clauses, and if we fail one of them, then we don't do it. Okay, it's not you don't do it, because then you're making decisions based off of biased information, which is not what you want to do, and it's not accurate. All right, cafeteria. Let you do number 7 there. Latoya wants to estimate P, the proportion of all students at her large boarding school that like the cafeteria's food. She interviews a simple random sample of 50 of the students at the school and find that 14 like the cafeteria food. Check to see if the conditions for confidence interval are met for calculating it. So, real quickly, check them. Write down your supporting information there. Again, you're going to have tonight for homework where it's going to give you options. It is, or the conditions were met or were not met. And you're going to have to pick the reason why. They both met it, the things, or one of them failed it. Okay? If I made you turn in like paper homework, then you'd be writing those out for me. Do what? You have to explain why? Uh-huh. No, I think it's the ones I chose were a drop down, so you get to pick. Or it may say both, but I think I picked drop down ones. Okay. All right, there was an SRS of 50 students, so we met the random clause. Again, for my AP kids, that's all I have to write on the AP test on a free response. When they're asking you to check this whole thing for a confidence interval, they say, hey, random, and they put down SRS of 50 students. All right. If they don't get points for that part if they don't show that they met the condition. Large count. So with that in mind, is NP hat greater than or equal to 10? And is N times 1 minus P hat greater than or equal to 10? So is 50 times 14 over 50 greater or equal to 10? That's a yes. 14 is greater than or equal to 10. 50 times 36 over 50. That gives me 36 greater than or equal to 10. So we meet. Both conditions are met. So we can construct a confidence interval. Take a peek at number 9. So I know I skipped over 8, but take a peek at number 9. So number 9 says, contact your representative upset with the proposed new law to state. Ryan emailed his representative in the legislature to express his disapproval. The representative emailed back saying that only 2 of the 200 messages had received that opposed the proposed law. Check if the conditions for calculating a confidence interval met. First off, do we see anything about a simple random sample of 200 messages? No. So we failed there. Second, if I do 200 emails times 2 over 200, which is the P hat, is 2 greater than or equal to 10? No, so we fail that one too. Okay, even if we thought, okay, yeah, maybe, even if they said that there was a simple random sample of 200 messages, fantastic. We would fail on the large count one. Okay, so this one fails on both because they don't tell us how the emails were like he got them. He just said out of 200 emails, he got 2, and so forth. We just don't know. If he said it was a simple random sample of 200 emails, then we'd be okay for the random clause. All right, next part. Calculating critical values. This is a new thing. So if you're distracted and not focusing on me, this is where we want to make sure we tune back into Mr. Stevens. There's 2 ways that we can calculate critical values. We need a critical value for our confidence interval calculation. We need them when we do hypothesis testing as well. So this is not the only time. The nice thing is, even in the video on Friday, she said we can construct whatever type of confidence interval we want. We can do a 67% confidence interval. There are ones that are used more often. 90%, 95%, and 99% are usually the 3 most commonly used. Okay, especially for testing, purposes and so forth. And the way we associate that with is when I had you guys interpreting if there was significant evidence about something, what percent did I tell you to pay attention to or compare to? What? Yeah, 5%. Okay. So what's 1 minus 5%? So a 95% confidence interval is equivalent to when we compare something for evidence for 5%. The other two most common ones that they use are 10% and 1%, which would be a 90% confidence interval and a 99% confidence interval. Okay? When we get the hypothesis testing next chapter, they'll tell us that we have a perform the test and compare it to either 1%, 5%, or 10%. So typically, I will say this is where the math nerd in me comes out. When we're dealing with those three most common, I just memorize the critical value for each one, and then I don't hit the calculator. When you're using it so much, you just say, oh, I'm going to use this one, I'm going to throw these numbers in. I get it memorized. Okay? Just to save time stepping as we're doing things. Now, how do we find this section? We deal with what's known as Z star. And when we deal with means, we deal with one that's called T star. That one's a little bit more complicated. But since we're dealing with proportions, we call it Z stars. So what we do is as follows. Step number 1, we do 1 minus the confidence level and divide it by 2. Step number 2, we use inverse norm to determine Z value. So let's walk you through doing some of these. Problem number 11. Excuse me. Problem number 11. It says that we have a C level of 98%. So I'm going to do 1 minus 0.98 and divide it by 2. That's 0.02 divided by 2, which is 0.01. I'm now going to do an inverse norm. My area is equal to 0.01. My mu is 0. My standard deviation is 1. Again, the reason why we can go ahead and fill those in, if we're finding our Z value means that we're on a normal curve. It's been standardized. So, on my handy dandy little calculator that's somewhere around here, and I have to reset it because I just wasted too much time. And you can work ahead of me on this one. Oh, give me a freaking break. There we go. That's what I want to get rid of. I want that one. I want that one. Oh, that's not what I want. Son of a biscuit. There we go. That's what I want. One of these days I'll catch up to you. All right, all caught up here. All right, so with that in mind, second vars, number 3, type in 0.01. Leave those alone. Leave it as left. Hit enter a couple times. So for number 11, my Z star is 2.32634787. Now, on the homework, they'll probably tell you to round to the third decimal. When we go to calculate our confidence interval, we want to use as many decimals as possible so that we can stay accurate to the 4th or 5th decimal place. Okay? So I went through, as you do the second part of our lesson here in a minute as we do the confidence interval calculations, I went through and calculated by hand the answers to see, okay, what did the book want? What did they want online? And if I took the rounded 3-digit decimal, I didn't get the answer they wanted. I was off by a little bit outside of the plus or minus point whatever. So when I went through and kept 5 or 6 or 7 decimals and did it, I got exactly what they wanted when I rounded. Okay, so right now, when you answer the questions, what's the Z-star or critical value? Round it to the 3rd decimal. When you get to the problems where they tell you to calculate the confidence interval, like we're going to get to, use all the decimal, and then you'll be fine. Okay. All right. So now let's do that for the next ones. All right. You can work ahead of me. I'm going to do 12 by hand again, and then I'm going to throw down the answers for 13 to 14 to see if you do it. Again, it's a quick calculator activity is really what it becomes. Again, I want to find a Z for a 96%. So 1 minus 0.96 divided by 2 is 0.04 divided by 2 is 0.02. Inverse norm, 0.02, 0, and 1. All right, so that's what I got for that one. Please do the other two. I want to make some connection here in a minute, so I need you to have all of those down there. For the last two, you should get something like this. Again, I just grabbed those out of the book. Again, the online thing likes 3 decimals. I like 4 because my AP class, they have to do 4, so I just try to keep it all the same. That's why all my online stuff is set to 4. Now, which percentage had the smallest answer? Which was what percent?
Or the smallest percent.
Yeah, 13 had the smallest percent, right? 93%. And it had 1.8212. Okay. Which one had the biggest answer? 14. The 99.9%, which is almost 100%. Okay. It had a Z-star of 3.2. So the bigger the percent confidence level, the bigger the Z-star answer. Okay. The smaller the confidence level, the smaller the Z-star is. Okay. You may have those questions where it says, hey, if you increase the confidence level, how is that going to affect the critical value? If I increase my confidence level, then my critical value increases. If I decrease my confidence level, then my critical value is going to decrease. So those are some of those little sidebar questions that could be asked. And they're just like when they talk about, how does the margin of error change when you change the confidence level? Good thing about it. Since we're dealing with Z, which is basically a Z-score, and on the normal curve, isn't the Z how many standard deviations away from the middle or the mean we are? So I had that one connection somebody asked last year. They said, you know, in a way, are these kind of like percentiles? And they are. They're kind of like percentiles. And so, you know, we're finding out if we're doing this, you know, what is the z-score associated with that percentile with the stuff to the left? And it's roughly how many standard deviations you're away from the center is what you're doing. Did you guys notice that I didn't say anything? We dropped a negative when I wrote the answer. Okay. And again, that's just standard, and the reason behind it is we're going to see the formula here in a second. The formula for what we're doing says p hat plus or minus z star, and then square root of whatever. Well, it doesn't matter if z star is negative or positive. If you have it as a negative, well, a negative makes a plus, and a positive negative makes it a negative. So we just drop the minus sign off of the z star when we go to talk about it as a critical value. Because since we're doing it twice, once with the plus and the minus, they just kind of negate each other and stuff. So that's where they're always written in positive, is what they're written as. All right, so again, when doing homework, I wrote this note, when doing homework, need to use the formula I'm getting ready to show you. Keep all the decimal places for accuracy. And again, the reason why I say that, we found that out with the last chapter. They like doing stuff using everything as a z-score when they did the last chapter on some of those probabilities. So as I worked some of the problems, I went through and said, okay, how are they grading it? By which aspect? And so that's why I put that tip there. They want you to use this formula. As I get to teach a technology in the next section, then we can open it up to the technology piece. But I'll always double check. I've already created everything for the rest of the week. All the homework assignments and everything. So I got bored this weekend and did that for this class for the rest of the week, my calculus class, and then my college algebra class. I did it for the whole rest of till Thanksgiving and stuff. So little connections here. Let me blow up on this formula. Remember, p hat, that's our point estimate. That's our point estimate right there, p hat. Z star, again, that's our critical value. That's what we just spent time calculating. And then the whole square root part, that part right there, that is known as the standard error. Now, last chapter, we learned that was the standard deviation of a sampling distribution. All right, so we've been working with that formula. The only difference is instead of having p's in there, we got p hats. That's the only difference. So, you know, so we're taking that standard deviation of a sampling distribution, which is also now known as our standard error. In either case, whether it's today's case or the means, that little square root fraction part thingy is your standard error. Your margin of error is based off of the critical value times whatever that thing is. So here's a more formal definition for standard error, in case you need to see if you see the S, capital E, p hat, they want to know what's the standard error. And then we finally get to get down in here and actually do a couple confidence intervals by hand. So going back to the allergies, they want us to calculate a 95% confidence interval for P. We're assuming all the conditions are met. So we can go straight into the formula is what they want us to do on these first couple. So with that in mind, my P hat is 84 out of 227. I have my C level is 95%. So I need to figure out what my Z star is for that sucker. Now, we haven't played with 95% yet, so we can't just scroll up and pick it out of one of the other problems. So we need to go ahead and do that one there. So we need to say, okay, what is 1 minus 0.95 divided by 2? So 0.05 divided by 2 is 0.025. And then I need to do an inverse norm. 0.025, 0, and 1. That should give me something like 1 point. Is it 94996.3? Where's the 5? Where the 4 is? Okay, 195. Trying to remember my memorizing there. 1.9599638. Is there a 4 after that 8? A 6? Okay. So that's enough decimals. Okay. Is it 6911? Out of curiosity. Or is it just 6? Okay. So that's enough to get us accurate here for the homework problems. That many decimals there. I know it's a lot, but that's okay. We're big kids. So with that in mind, as I go to find my confidence interval, P hat plus or minus Z star. I like writing it down so I have it. P hat times 1 minus P hat over N. All right. So 84 over 227 plus or minus 1.95996,386 square root. Now again, since those are not terminating decimals, I leave them in fraction form. I'm going to type it all in that way in the calculator here in a minute. So 84 over 227 times 143 over 227. All of that over 227. Now the reason why I did that is because some of the stuff I like to test with is which is the correct setup. Not what the answer is, what's the correct setup. So that's the reason why I wrote that the way I wrote it. So if you did not write that down, I'd suggest you write it down. Because not always do I ask you to find the answer, sometimes it's what's the correct setup. The AP test does the same thing. Some of my questions are based off of AP questions for multiple choice when I decide to put one on there. You will not have to type that in by hand. It'll be you recognizing it on a problem. Because I do give you multiple choice from time to time, don't I? Okay? So, to say, because again, I would never ask you to type all that crap in. But, you know, I want you to be able to spot the correct setup. So now that I have that there, now I'm ready to break out my handy dandy little calculator on the center screen. I'm going to start with the square root part first. Second x squared alpha y equals, give me a fraction in there. I have two fractions on top, so I'm going to do an alpha y equals again, and I'm going to type in the first fraction. 84 over 227. Arrow to the right times, now another alpha y equals, and give me another fraction. 143 over 227. And then put a 227 on the bottom. Now, here's the thing as you look at the correct setup. Some of those multiple choice questions, they'll leave off the 227 right here, or maybe they put the 84 times 143 on top. Okay, so they'll have some little distortions of what's going on there. Okay. Just be careful. Okay. Just be careful. I'm going to go ahead and hit enter now, and I'm going to leave that decimal on the screen, and I'm going to write stuff down here as I'm showing my work. I have 84 over 227 plus or minus that big old 1.95996 386 times now 0.0320456,346. I'm now going to multiply in my calculator times now the 1.95. 1.95996,386. Hit enter. So I have 84 over 227 plus or minus 0.0628082856. Now I'm going to say, all right, give me a fraction. Alpha y equals 84 over 227. Arrow to the side. And I'm going to tell it to add that last answer to it. And I'm going to hit enter. So this tells me the upper bound. Now I'm going to round 0.4329. Now I'm going to round it to the fourth. I'm going to go back in there and do second enter to get my last thing I did. I'm going to change the sign to a minus, but I can't do answer. I got to get rid of that and then arrow up and find that 0.03 decimal. No. Yes, no. I want the 0.06 decimal. That's the decimal I want. 0.06 decimal. And then hit enter. And that tells me the lower bound is 0.3072. So we're 95% confident that the interval from 0.3072 to 0.4329 contains the true proportion of all students who completed the census at home school survey who have allergies. So that's tying in the wrap-up that we did on Friday. That's how we would interpret it. Don't have to do it today, but that's what we're going to be doing tomorrow a lot as I teach you the four-step process. I think number 19 actually gets you to interpret it, so write that little statement there as well. Oh, there you go. So customers have walked into something. So here's one about Jordan. In her first grade social studies class, Jordan learned that the 70% of the Earth's surface is covered in water. She wondered if this was true and asked her dad to help. To investigate, he tossed an inflatable globe to her 50 times, being careful to spin the globe each time. That helped with the randomness, is what that did. When she caught it, she recorded where her right index finger was pointing. In the 50 tosses, her finger was pointing to the water 33 times. Calculate a 95% confidence interval for the proportion of Earth's surface that is covered in water. Assume the conditions are met. Great, we don't have to test it. Again, the spinning was for the random part. The 33 out of 50, if we went through the process of the NP hats, we would have seen that it would have met anyway. So they just asked us to go figure it out. So what is the confidence interval? So P hat is 33 out of 50. Now that's a terminating decimal. So I'm going to go ahead and make it 0.66. I'm going to go ahead and make that since that's a terminating decimal, instead of having to write the fraction in those places, I'm going to use that version to make things go smoother. So now I need my Z star. Well, we are fortunate. We know what it is, 1.95996,836. We had that in the previous problem. So we can go ahead and use it. And then now we're ready for our formula. 0.66 plus or minus that long decimal times the square root of 0.66 times 0.34 over 50. Again, you can use the 33 over 50, but to me, if it's not a terminating decimal, leave it as a fraction. This one was a quick terminating decimal at two places, so that's why I went ahead and converted it. And then now I'm ready for the calculator. So second x squared alpha y equals 0.66 times 0.34 over 50. So 0.66 plus or minus 1.9599 6.6836 times 0.0698856208. I'm going to now hit times 1.9599 6836. So this is 0.66 plus or minus point. Did I have happy fingers? Did anybody get that same answer? Out of curiosity. You know, sometimes my fat fingers hit different things. Did anybody get that same answer? Ah! I see where mine's off. Anybody see where mine's off? 6386, and I put 836. I reversed my Z number. All right, so I want to take that decimal and multiply it by 1.9599 6386. 6386. There we go. So that should be a 6386. 386. That's why it didn't look like last block. Okay. All right, so 0.136973, that's enough there. So 0.66 plus the answer tells me the upper side is 0.79. That one actually rounds. It's 79697, so that's really 0.7970. And on the lower side, 0.66 minus that answer, which would be 0.5230. All right. So we're 95% confident that the interval from that to that captures the true proportion of the Earth's surface that is covered in water. That's how we would interpret it. Okay? So homework's out there live. It's got about 15 questions on each of the different sections there.